In this lesson, we're going to talk about derivatives of logarithmic functions. Before we start taking derivatives, though, I want to do a quick review of logs. So we'll start with this definition. It says b is positive, not equal to 1. The exponential function, b to the x, is either increasing or decreasing, and so it's 1 to 1. It therefore has an inverse function, which is called the logarithmic function with base b, and is denoted by log base b of x. And this is log form, and you can rewrite it in exponential form. So in log form, it's log base b of x equals y. In exponential form, it goes base b raised to the y exponent equals x. And I put a note here, we have the mathematician John Napier. He was Scottish, and he was known for being a mathematician, a physicist, and an astronomer. And he was best known for discovering logarithms. So here's his photo. All right, so next we have our cancellation equations. If you have anything of the form log base b of b to the x, these are the same, so then this expression just equals x. If you have anything of this form, b raised to the log base b of x, where these are the same value, then they undo each other and you just have x. Next we have our log properties. First we have log base b of x times y. You can split this up to log base b of x plus log base b of y. If there were 3 things in here, you would have 3 different logs. Next we have log base b of x divided by y. You can rewrite it as log base b of x minus log base b of y. So whatever's in the denominator, that log gets a negative in front. And then finally, we have log base b of x to the r. If you have an exponent, you can move the exponent and multiply it to the front. So you can rewrite this as r log base b of x. And we'll be using these properties to manipulate the log expressions before we take their derivatives. Here we have the definition. It says the log with base e is called the natural log and has the notation. So when you have a log specifically with base e of x, you're going to write it as ln of x. So here we have some characteristics of natural log. When you have ln of x equals y, you can rewrite it from log form into exponential form as e to the y equals x. If you have ln of e to the x, these undo each other and you just have x. If you have e raised to the ln of x, those undo each other and you just have x. And finally, ln of e is 1 and ln of 1 is 0. So now we're going to cover derivatives. We have this note here. It says, we know that the function y equals e to the x is differentiable. Therefore, we know that its inverse, y equals ln of x, is also differentiable. So we have the formula d dx of ln of x, meaning the derivative of ln of x is equal to 1 over x. Here's the proof. It says, let y equal ln of x. Then we know that we can rewrite it as e to the y equals x. Differentiating this equation implicitly with respect to x, we start with e to the y equals x. We take the derivative with respect to x, so you just get e to the y dy dx. The derivative of x is 1. Then if we isolate the dy dx, we'll get 1 over e to the y. And then because e to the y is equal to x, we can plug that in and we get 1 over x. When we take the derivative of functions with ln of x, it's not always going to be just x, so we're going to also need to be able to apply the chain rule. So I have it written out here. The derivative with respect to u of ln of u is going to be 1 over u, and then you would times by du dx. I also have it written out here. If you're taking the derivative of ln of some function, you're still going to go 1 over that function, but then you chain rule, so you times by the derivative of the inside, which would be times by g prime, but we can put that g prime in the numerator. And here I have our differentiation formulas written out for this lesson. We have the derivative of ln of x is 1 over x. We also have the derivative of log base b of x is equal to 1 over x ln of b. And finally, I have the derivative of a to the x. It's equal to a to the x ln of a. And we're going to use these formulas to be able to differentiate these next problems. This first example, we have y equals ln of x cubed plus 1. So since we have ln of a function, to take the derivative, we do 1 over the function, and then we chain rule. Because this isn't just plain x, we take the derivative of it, and we get 3x squared, and so we multiply that to the end, and here's our final answer, 3x squared over x cubed plus 1. Next, we have f of x equals ln of sine of x. Again, to take the derivative of ln of a function, it's 1 over that function, and then we times by the derivative of the inside function. So the derivative of sine is cosine, and you can either times that at the end or you can put it right to the top. Either way, we get cosine over sine, and that can be rewritten as cotangent of x. For this example, we have g of x equals the square root of ln of x. So the first step is we rewrite this as ln to the 1/2. To take the derivative, we're going to apply the chain rule. So first we're going to bring the 1/2 to the front, leave the inside function the same, and then we subtract 1 from the exponent to make negative 1/2. Next, we're going to times by the derivative of the inside function. So the derivative of ln of x is 1 over x. So at this point, this has a negative exponent, so I'm going to bring it down to the denominator. And finally, we're going to rewrite this with a square root. So here's our final answer, 1 over 2x, the square root of ln of x. For this example, we have g of x equals ln of, and then we have e to the x plus ln of x. Our outside function is ln, so to take the derivative, we're going to go 1 over this inside function. Next, we're going to times by the derivative of the inside, and we're going to write it in the numerator. The derivative of e to the x is e to the x, and the derivative of ln of x is 1 over x. At this point, we want to make this numerator one big fraction. So these guys need common denominators, so we're going to multiply this by x over x. So we have x e to the x plus 1 all over x, and then that fraction is still being divided by e to the x plus ln of x. Now we're going to take this fraction, divide by this one, which is the same as multiplying by its reciprocal, or we can think of it copy dot flip. So right here I multiplied by the reciprocal, and then finally we're just going to multiply these fractions across the top and across the bottom. So here's our final answer. For this example, we have y equals ln of x plus 1 over the square root of x minus 2. So if we tried to take the derivative of this like we did in the previous problems, we would be going 1 over, and then we'd take this fraction, put it down here, but then we'd have to times by the derivative of the inside, which would require the quotient rule, and it would get pretty crazy. So instead, first we're going to manipulate this. Ln of a fraction is the same as ln of the numerator minus ln of the denominator. And we're even going to take this a step further. Instead of a square root, we're going to rewrite it as quantity to the 1/2. And then one more time, by properties of logs, we're going to move this exponent to the front of the natural log. So now we have this expression that we can finally take the derivative of. So by first manipulating, once we get to here, this is going to be a lot quicker for taking derivatives. The derivative of ln of x plus 1, we're going to go 1 over the function. And then when you chain rule, the derivative of the inside is just 1, so that's what goes on top. Over here we have minus 1/2 being multiplied in front, so we can drop that down. To take the derivative of ln of x minus 2, you're going to go 1 over that function. And again, when you chain rule, the derivative of x minus 2 is just 1. So now we have two fractions, and we're going to make common denominators. Each denominator is different, so we're going to multiply them by each other. So right here we have 2 times the quantity x minus 2, so when we distribute the 2, we get 2x minus 4. Over here, 1 times x plus 1 is just x plus 1. And finally, since we have common denominators, we're going to combine like terms across the top. And right here, be careful because it's minus both of these terms, so we're going to distribute the negative. So we have 2x minus x is just going to make 1x. And then we have minus 4, and it's minus 1, which is going to make minus 5. So here's our final answer, x minus 5 over 2 times the quantity x minus 2 times x plus 1. This example says f of x equals ln of the absolute value of x. So we're going to take the derivative of this, but first we want to rewrite this using the definition of absolute value. Since f equals ln absolute value of x, I have f equals, and remember by definition of absolute value of x, the absolute value of x is equal to positive x for x greater than 0, and it's equal to negative x for x less than 0. So we leave the ln, that doesn't change, but again the absolute value of x gets replaced. So now when we take the derivative, we're going to take the derivative of each part. The derivative of ln of x is going to be 1 over x. The derivative of ln of negative x, we're going to go 1 over this function. Then we take the derivative of the inside function, which is negative 1. And you can see right here this is positive 1 over x, and this also reduces to positive 1 over x. And again, for x greater than 0 and x less than 0, since they're both equal to 1 over x, I wrote, therefore, f prime of x equals 1 over x. And then I used some notation. We have for all x that are an element of the real numbers. Again, the upside down a just means for all. So we have for all x that are an element of the real numbers. So that just means for all real numbers such that x does not equal to 0. For part G, we have f of x equals log base 10 of 2 plus sine x. So I wrote the derivative of log base b of x for reference over here, and it's equal to 1 over x ln of b. So in this problem, we have base 10, and I want to emphasize again, this formula says log base b of x. So you go 1 over x ln of b. So whatever's right here, we put it right here. So in this problem, instead of x, we have 2 plus sine x. So first I just set this up. Instead of x here and here, we have 2 plus sine x that goes right here. Then the formula goes ln of b, so we go ln of, and the base was 10. So again, because this isn't just x, we're going to chain rule. So that means we're going to times by the derivative of its inside function. The derivative of 2 is 0, and the derivative of sine is cosine. So for our final answer, we get cosine of x over the quantity 2 plus sine x times ln of 10. For this example, we have y equals log of x over the quantity x squared minus 1. Before we take the derivative using this formula up here, first I want to rewrite this. We had a quotient, so we rewrite it as log of the numerator minus log of the denominator. So now we're ready to use this formula. Remember, if the base isn't written, then it's implied that it's base 10. And I just wrote that note out. If there's no base, then it's implied base 10. So right here we have log base 10 of x. So using this formula, we're going to go 1 over x ln of 10. Next we have log base 10 of x squared minus 1. So we're going to take this x squared minus 1 and we put it right here. Then we go ln of 10. And because this isn't just x, we're going to chain rule. So we times by the derivative of the inside function, which is going to be 2x. And I'm going to write that right on the top. Last step, we're going to rewrite these into one fraction, so they need common denominators. So that means we're going to multiply this fraction by x squared minus 1 on top and bottom. And then over here, we're going to times this fraction by x on top and bottom. Okay, so I got that set up. And then finally, when we combine like terms across the top, we have x squared minus 1 and then minus 2x squared. And we're going to combine these two like terms to get negative x squared. So our final answer is negative x squared minus 1 all over x times x squared minus 1 times ln of 10. For this example, we have y equals 10 to the tangent of x. So we have a function in the form of a to the x. This isn't just x, it's obviously tangent x. But a is 10, and then instead of x, we have tangent of x. So I have the derivative written over here, the derivative of anything of the form a to the x, where a is the constant and the variable's up here. It's equal to a to the x ln of a. So again, in this problem, we have a is 10, and then instead of x, we have tangent of x. So according to this formula, our derivative is that same thing, so 10 to the tangent of x, and then we times by ln of a, which is 10. And finally, because this isn't just x, we're going to chain rule. The derivative of tangent is secant squared, and there's nothing to simplify, so that's our final answer. It's just 10 to the tangent of x, ln of 10, secant squared of x. For this next one, we have f of x equals 2 to the x times cosine of x cubed. Because you have two x's in two different places, this is a product, so we're going to use the product rule. So first, we're going to take the derivative of 2 to the x. Again, the derivative of a to the x is a to the x ln of a. So we have 2 to the x, so the derivative is going to be 2 to the x ln of 2. Over here, the derivative of cosine of x cubed, we take the derivative of the outside function, which is negative sine, leave the inside function the same, and again, by the chain rule, we times by the derivative of the inside function, which is going to be 3x squared. And to apply the product rule, we're going to multiply these, and then we add the product of these. Last step, I'm just going to factor out this 2 to the x. And because this is negative, I moved this part of the problem over here and then wrote this part right here. So there's our final answer. The last concept in this lesson, we're going to talk about logarithmic differentiation. So to do logarithmic differentiation, I wrote out the steps. First, you take the ln of both sides, and then you use properties of logs to simplify. Then you differentiate implicitly with respect to x, and finally you solve the equation for y prime, and then substitute the y back in. Before doing an example of logarithmic differentiation, first I wanted to look at the 4 cases of exponents with bases. So first is, if you have the derivative of anything where you have a constant to a constant, the derivative of a constant is 0. If you have a problem where you have a function raised to a power, which is a constant, you're going to use the chain rule. You bring the power to the front, you leave the inside the same, you subtract 1, then you times by the derivative of the inside. If you have a constant to a variable, which is just like the problems we just did, like a to the x, you're going to go a to the x ln of a. If it's not just x, then you chain rule, so you times by the derivative of the inside function. And finally, if you have a function to a function, so again, if you have a function with x and then you have an exponent that also has x, you're going to use logarithmic differentiation and you're going to follow these steps. This example says use logarithmic differentiation to find the derivative of the function. We have f of x equals x raised to the 1 over x. Because you have a variable raised to a variable, you're going to use logarithmic differentiation. Before we get started, I'm just going to rewrite this as y equals. Step 1 for logarithmic differentiation says we're supposed to take the ln of both sides. Within that same step, we're going to use properties of logs to simplify. So we have an exponent, so we're going to multiply that to the front of the ln. Because we're about to take the derivative, I'm going to rewrite this as x to the negative 1. All right, so step 2 says take the derivative implicitly with respect to x. So first right here, the derivative of ln of y is going to be 1 over y, and then we're going to times by y prime because it's a non-x term, and we're taking the derivative implicitly with respect to x. Here we have a product of functions, so we're going to apply the product rule. This is really 1 over x, so when we multiply these together, you have 1 over x times 1 over x, which makes 1 over x squared. Then we add the product of these. This is really negative 1 over x squared, so negative 1 over x squared times ln of x. We can write that as negative ln of x over x squared. And because these have common denominators, I'm going to rewrite it as one fraction. For the last step, we're going to isolate the y prime. So our final answer is x to the 1 over x times this quantity. This example says y equals tangent of x to the 1 over x. So first step is we take the ln of both sides. Next, we're going to move this and multiply it to the front. And then I rewrote this as x to the negative 1. For step 2, we're going to take the derivative implicitly with respect to x. So the derivative of ln of y is 1 over y, and then we times by y prime. Over here we have a product of functions, so we're going to use the product rule. The derivative of ln of tangent of x is going to be 1 over tangent of x. Then we times by the derivative of the inside, which is secant squared x. When we multiply these, remember this is really 1 over x. And over here when we multiply these, this is negative 1 over x squared. And in this problem, I'm actually just going to leave these separate and not turn them into one fraction. And for our last step, we want to isolate y prime, so we're going to multiply both sides of the equation by y. So I wrote y times this whole expression. And our very last step is we don't want to leave this y here. We go to the original problem, and y is equal to tangent of x to the 1 over x. We're going to substitute this in right here. So here's our final answer. Thanks for watching, guys!